A gente está num período de convergência, né? O Robert falou muito sobre como a tecnologia está entrando no nosso corpo e também existe o contrário, né? O nosso corpo entrando na tecnologia. E um exemplo disso é o armazenamento de dados, como música, poemas, até mesmo a Wikipedia, dentro do nosso DNA. E justamente para falar sobre um futuro possível para o armazenamento de dados digitais com o DNA, é que eu vou chamar a nossa próxima palestrante, ela que é americana, cientista bioinformática, foi inspirada a aprender bioinformática e dar vida a dados biológicos. Ela tem graduação em Biology of Neurodegenerative Diseases, Genomics, Biotech, em Harvard. Ela é Masters em Bioinformática pela Brandeis University e também atua no Institut Curie, em Paris. E só para vocês terem uma noção, a palestra dela no TED Global teve mais de 1,5 milhão de visualizações. Eu quero chamar aqui a Dina Zielinski. You're very welcome.
So I'm a bioinformatician, bioinformatics scientist, however you want to say it. Many of you might actually be wondering what that is. Most of my job actually involves working with scary files that look like this. These files are often tens of millions of lines, and if I tried to work with them on my computer, it would probably crash, even with my fancy new MacBook. And so I'm always worried about running out of space on the server, because these files take up terabytes of space. Now, on a more relatable level, most of us don't really think about how much data we're generating and where all this data is going. So here are just some ideas of how much data is generated by the minute. So all of you out there taking pictures, posting your Instagram story, where do you think all of that data is going? I mean, this is a crazy amount, 156 million emails sent in a minute. 4 million videos on YouTube are streamed. Where does it all go? Well, we all have this idea of some mystical place called the cloud. Now, your data is not really floating up in the air above you, as lovely as that sounds, and as convenient as it would be. In fact, all of those YouTube videos, all of your emails, photos, they're stored in server farms in rooms that look like this. Now, server farms require a ton of energy. So all of this data we're generating is actually pretty terrible for the environment. We don't really think about our eco-footprint when we're just generating and storing data. So you might be pleasantly surprised to know that Facebook is trying to make a difference. This is their server farm in Sweden. Now, the reason it's in Sweden is not because it's cheaper real estate. It's actually because it's not too far from the Arctic Circle. So instead of using electricity to cool all of these servers that get really hot when they're storing all that data and processing all of that data, they can sort of open the windows and let that Arctic breeze flow in. They're also using alternative forms of energy. So the footprint is largely reduced, but these server farms still are quite harmful to the environment. And of course, recycling all of that equipment, as servers don't actually last forever, they only last maybe tens of years, all of those thousands of servers eventually get tossed. So most of us would love to see this, inbox empty. Now, a lot of users back in 2011, a few 100,000 Gmail users, opened their inboxes and saw nothing and freaked out, because due to a software update, all of their emails, which were backed up on multiple servers, were gone. Fortunately, they were backed up on magnetic tape. It might surprise you because we don't actually use it anymore, but most of our precious data, including at giants like Google and Facebook, is actually backed up on this technology that was developed, back in the 1950s. And it's still the most reliable. So Google is actually able to recover all of those users' emails, happily for them. So it turns out that most of the world's data has been generated in the last few years alone. We have officially entered in what we call the zettabyte era. Now that's incredible if we continue on this trajectory because we're actually running out of storage devices. All of this manufacturing of servers and whatnot cannot keep up with this deluge of data that we're generating. So that's a lot of zeros. That's really what you need to keep in mind for most of my talk here. Now, most of us are used to working with data in the megabyte, maybe the gigabyte range. Some of you, if you're, for example, a photographer or a data scientist, might be used to working in the terabyte range. And most of us don't really even know what extent or what scale a petabyte or exabyte even is. So just for those of you who aren't familiar, a bit is just a 0 or a 1, a binary digit. And it takes 8 bits in a byte. So the point is that we're working with very large-scale numbers, millions, billions, trillions of ones and zeros. So since we're all talking about space here, I couldn't not talk about space. Most of you might remember this image. It was published back in April. It's the first ever image of a black hole. I actually think this image is in some ways equally impressive as that black hole image. And that's because this shows how all of the data was collected to generate that image. It was many telescopes on 4 different continents that collected data over several days. And in the end, they were working with 5 petabytes of data. And that stack of hard drives that MIT graduate student is in front of is only a fraction of that data. And it turns out that they actually had to ship those hard drives instead of sending it over the internet because it would have been too costly and would have taken up to several months to actually send it. So there's a joke that FedEx actually has a better bandwidth than the internet, even in 2019. So if you were not in diapers in the 90s, you probably remember seeing this somewhere. This is Bill Gates, the CEO of Microsoft. And this was in 1994, and the caption read, "This CD-ROM can hold more information than all the paper that's here below me." Now, in 1994, this was super impressive. And relatively speaking, that's quite a lot more data that you can fit on this tiny CD-ROM compared to all that paper. But if I handed anyone a CD-ROM, most of you, if you have a new computer, can't even play the CD-ROM. And most of you probably also only ever used it to make a more modern-day mixtape. I know I did. So we've come a really long way in improving man-made technology. The thing is, though, if I handed you a floppy disk, you certainly wouldn't know what to do with it. Some of you in this room, which makes me feel really old, might not even know what a floppy disk is, or maybe have never used one. And the thing is, we can actually more likely recover data from stone tablets and books than we can from a floppy disk, which was a technology that was used in the 1980s, not that long ago. So these technology become obsolete very quickly. Not only do people not even know what it is, but we have no way to use it. And that's because any new man-made device usually requires a new way to read it. This is why we don't have floppy drives in our computers anymore, or even CD-ROM drives. So you can also repurpose some of these devices. I was a big fan of floppy disks. But really, the data generation is completely outpacing all of the man-made technology, despite the fact that we're no longer using floppy disks, that we have very sophisticated new media to store data. Now, you all know where I'm going with this, or you have a good idea, but I had to build up some of the motivation for why there's actually a much better solution that was not even made by man. And since we like to juxtapose the past and the future here, it turns out that the best current solution for storing data has actually been around for billions of years. And now the storage density of DNA compares to no single man-made device. No man-made device can come near to how much data can be stored in DNA. And I'm going to quickly show you some of the advantages of DNA and why it makes such a good storage device. So if we take our own genome has 6 billion base pairs. Now, if you do a little bit of simple math up there, don't worry too much about it, you can fit the equivalent of 1.5 gigabytes of data in a single cell. Now, the average human has about 30 trillion cells in their body. So that's 1.5 gigabytes multiplied by 30 trillion. That's a lot of data. No man-made device can come anywhere near that amount. So as I mentioned, DNA has been around for a while, billions of years. And the reality is that any living organism is essentially a DNA storage device. Now, when I mention this, most people will often go to the direct question of, well, so can I store the data in my DNA? And my response is, well, you could, but our DNA already contains all of the information that's necessary to make us who we are. It's not exactly something we want to mess with. And so it's much safer to store synthetic DNA in a tube, as opposed to trying to store your family photos, for example, in your own DNA or in your own thumb drive. So DNA is actually highly robust, too. Most man-made devices last on the order of tens of years, maybe 50 years if you have some magnetic tape locked away somewhere safe. But DNA, we know, can be recovered thousands of years later. And we know this because DNA was recovered from an Iceman who lived around 3300 BC, and he was found in the Alps between Austria and Italy. And scientists were actually able to recover DNA from him and even find living relatives in Austria. So really, we can recover more meaningful data from this guy who lived thousands of years ago than from an old cell phone that's maybe 1 to 2 years old. So this is the first ever photo of DNA. It might not really look like DNA. It's called Photo 51, but this is the photo that really showed us the double helix structure of DNA. And that was published in 1953. Just a few years later, IBM released the first commercial hard drive. This was in 1956. And this monster could hold almost 4 megabytes, which is about one MP3 song. One MP3 song for 10,000 US dollars. It's not very impressive, but it really is the best that we can do at the time. And again, this was in the 50s. And now, 60 years later, we've really miniaturized all these devices, and it's quite impressive how far we've come. Even still, man-made devices are simply not as impressive as DNA. So I want to give you a very brief history of DNA storage, because while it's the oldest storage device, it's actually the most recent storage device that's been proposed to store man-made data. So Richard Feynman, he was an American physicist, and he was the first to really come up with the idea of storing data in DNA and possibly miniaturizing biological functions and to improve their capabilities. And it was this guy, he was a Soviet scientist, Mikhail Niemann, who actually first coined the phrase of storing data in DNA. And soon after, my favorite is this guy, Joe Davis. He was a scientist at MIT, and he actually works currently in George Church's lab, the guy who's working on bringing back the woolly mammoth. So I think maybe they get along pretty well. So he did this art project where he took this ancient symbol called the microvenus, and he converted that into binary digits. And so if you convert this image into zeros and ones, it totals 35 bits. Then using a simple formula, he converts that into DNA, totaling only 18 base pairs long, so 18 A's, T's, C's, and G's. He then copied that into E. coli bacteria and grew it up in the lab. So he was really the first to actually store data in DNA, but he didn't actually recover the information stored on that DNA in the bacteria. So obviously, that's a pretty important step. So this is a brief timeline of the more recent advances. So the more recent advances in DNA storage were actually in the last 10 years. So one of the first improvements in scaling the technology was actually in 2010, where about 8,000 bits were encoded in DNA. And it wasn't until 2015 that scientists were able to do so without error. And in our work, which was published in 2017, which I'll talk to you a bit about, we reached the largest density to date at 215 petabytes of data per gram of DNA. And recently, a company in Boston stored all of Wikipedia, so about 16 gigabytes compressed, in DNA. But they didn't tell us how much it cost, which is kind of an important detail. So how do we actually store data in DNA? If you take that first ever image of DNA, that photo 51, we convert it into bits or binary digits. We can then store this in DNA. So anything digital, anything that is encoded as zeros and ones can be stored in DNA. It's actually quite simple, and the conversion between bits and DNA is the easiest part. So in the lab, we scientists can write DNA, synthesize, store it, and copy it, as well as read it through sequencing. So in our study, as I mentioned, we reached the highest density to date of DNA storage. And what we did is we explored what is known as the Shannon Capacity. Now, don't worry, I promise I won't bog you down in math. The reason I showed this equation is not actually to scare you, but it's actually to show you this very simple idea. So Claude Shannon was the father of information theory. He was an American mathematician, and he actually calculated the maximum the maximum amount of data that can be transmitted using this equation. So the capacity is determined by the bandwidth. Many of us are familiar with bandwidth if you have an internet connection at home, and as well as taking into account your ratio of signal over noise. And so this really applies to DNA because essentially DNA can be thought of as a communication channel as well. In the end, we're just trying to recover or send and receive data just as we stream videos. So I want to give a simple example here. Normally we work on the order of millions or trillions of bits, but let's say we want to send this message without error. So one thing we could do is we can repeat that sequence 3 times. This way, if an error occurs, we can still recover the original message 010. So for example, if we receive this message, there's clearly an error in there, but we see that the other 2 sequences are the same. So we can assume that the original message is 010. Now this is called error correcting code. It's not very efficient because imagine if you're working with millions of bits. It's fine if we're working with 3 here, but it requires 3 times the amount of information, which will take much longer to send over. So really longer code is much less efficient. So when we're storing data or transmitting data, whether it's digital or in DNA, it's really about trying to find the minimum amount of extra information, the minimum amount of bits that we need in order to submit the maximum amount of data. So we used an algorithm called fountain codes. This algorithm was developed in the 90s for noisy data transmission like mobile television. And so we applied this to our study where we were able to store data in DNA. So because DNA consists of 4 letters, A, C, G, and T, you can store a maximum of 2 bits of data per nucleotide. The thing is, DNA is not this just static media. DNA has a lot of biochemical constraints. So one thing that gives us trouble in the lab when we try and copy and read DNA is when we have a lot of C's and G's. Another is if we have a lot of the same letter repeated many times. And so this actually reduces the amount of data that can be stored in a single letter of DNA. Also, when we work with DNA, it's not just one long sequence of letters of A's, T's, C's, and G's. We usually work in short phrases of 1 to 200 A's, T's, C's, and G's. And so in order to piece back that original file, we need to know where each DNA molecule came from. So to do that, we need to add some more bits to barcode that molecule. So that gets us down to a capacity of about 1.8 bits per nucleotide. Now the fun part of this study was getting to choose which files we actually stored in the DNA. So one of them was the manuscript published by Claude Shannon, since after all we were exploring the Shannon capacity of DNA storage, as well as an operating system, a Pioneer plaque that was sent on the Pioneer spacecraft in the 1970s in case it ran into Martians, an Amazon gift card for $50 that a scientist in Switzerland was able to decode, and a zip bomb. This is a virus that if you unzip it, it keeps unzipping until it crashes your computer, just for fun. And the last thing we encoded was one of the first movies ever made. So once we did that, we zipped all these files up, compressed them, and we converted all of the zeros and ones to DNA, like I showed you, the A, T, C, and G to zeros and ones. And we sent that file, just an Excel file, to a company out in California. And this is the tube they sent back. All of those files were in that tube, all 2 megabytes of our data. So as I showed you, we can write, store, and read DNA. But there are, of course, a lot of pitfalls to DNA. One thing is that you have to actually destroy the DNA when you sequence it. So when you actually take the sample out of the tube and sequence it, you lose your information. The great thing is, though, we have this technology called PCR, where you can make basically infinite copies of your DNA in a tube in the lab for a few dollars. So we were able to do this to really test the process because copying can introduce errors. But we were still able, sorry, there's a video. So we were still able to copy the data trillions of times, and this is the movie that we stored. And even after all those copying, we were able to recover the video without any error. So as I mentioned, we reached a density of 215 petabytes per gram, the largest density to date. Now, if we consider all the world's data, which is projected to reach more than 40 zettabytes by next year, that means that all the world's data would fit into 160 kilograms of DNA. Now, I tried to look for a local object. This is the best I could come up with, which was actually convenient because a box of coconut milk weighs about 1 kilo. So it would take about 160 boxes of coconut milk if data was stored in DNA. So the problem with DNA, though, is that this had a pretty hefty price tag. There was not a lot of files that we stored. It's only 2 megabytes, and it cost $7,500 US to synthesize, and another $2,000 just to sequence it to get that data back. The thing is that even with magnetic-based storage, which is still the most reliable media, DNA is actually on pace to outperform magnetic-based storage within our lifetimes easily, possibly even within the next 10 to 20 years. So as I mentioned, DNA's biggest competitor is magnetic tape. And if you were to actually store all of the data, all the world's data, on some of these devices, you would need, for example, this is one of the highest end flash drives out there. You would need 350 million of them. And if you take one of the highest quality tape cartridges, so the magnetic tape, you'd need 160,000 of them compared to those boxes of coconut milk. Now, we make constant improvements on man-made technology. This is pretty impressive, actually. This is a thumb drive that can store 2 terabytes of data. The thing is, it costs as much as this fancy laptop I have up here. I mean, could you imagine losing that thing? Further, it only stores a fraction of the amount that DNA can store. That thumb drive weighs 136 grams, whereas we can store 200 petabytes in a single gram of DNA. And that fancy thumb drive can only last 5, maybe 10 years, whereas DNA can last hundreds, if not thousands, as we saw from the mummy. DNA, of course, has to be kept cold and dry, but we could, of course, store it in Sweden or maybe in your wine cellar. It doesn't necessarily need electricity. And so if we compare it with its biggest competitor, it stacks up pretty well, minus the fact, of course, that that price tag at the bottom there. It's not very convincing. No one's really going to want to buy this technology or use it personally. The thing is, we've made incredible advances in DNA sequencing technology. Just 18 years ago, it cost over $100 million to sequence one human genome. These days, it costs a few $100s. That's a pretty big advance for only 18 years. And the thing about man-made devices is this exponential growth can only last for so long. We can only miniaturize so much. DNA is already as compact as we need it to be. Further, most man-made devices quickly become obsolete. This won't be the case with DNA. So this is the progress that we've made with man-made devices back from 1956 until today. The miniaturization is incredibly impressive, but that's because we've focused so much effort on improving man-made technology. We haven't really done that yet with DNA. However, this is some of the advances we've made in miniaturizing the sequencing technology. So we really just have to give DNA a bit of time. Since that time that we started miniaturizing that gigantic hard drive, we've learned to read, write, copy, even edit DNA. So really, we may be storing our most valuable information in DNA sooner than you think. Obrigado.